Bismuth-antimonides, Bismuth-antimonies, or Bismuth-antimony alloys are binary alloys of bismuth and antimony in various ratios. Some, in particular by 0.9 SB 0.1, were the first experimentally observed three-dimensional topological insulators, materials that have conducting surface states but have an insulating interior. Various Bismuth-antimonide alloys also superconduct at low temperatures, are semiconductors, and are used in thermoelectric devices. Bismuth-antimonide itself is sometimes described as Bismuth-antimonide. Synthesis. Crystals of bismuth-antimonides are synthesized by melting bismuth and antimony together under inert gas vacuum. Zone melting is used to decrease the concentration of impurities. When synthesizing single crystals of bismuth-antimonides, it is important that impurities are removed from the samples, as oxidation occurring at the impurities leads to polycrystalline growth. Properties. Topological insulator. Pure bismuth is a semi-metal containing a small band gap, which leads to it having a relatively high conductivity. When the bismuth is doped with antimony, the conduction band decreases in energy and the valence band increases in energy. At an Sb concentration of 4%, the two bands intersect, forming a Dirac point. Further increases in the concentration of antimony result in a band inversion, in which the energy of the valence band becomes greater than that of the conduction band at specific momenta. Between Sb concentrations of 7 and 22%, the bands no longer intersect, and a bi-1xSbx becomes an inverted band insulator. It is at these higher concentrations of Sb that the band gap in the surface states vanishes, and the material thus conducts at its surface. Superconduct to the highest temperatures at which by 4 Sb 6 thin film of thicknesses 150-1350 a superconduct. The critical temperature Tc is approximately 2 K. Single crystal by 935 Sb 065 can superconduct at slightly high temperatures, and at 4.2 K, its critical magnetic field Bc of 1.60 at 4.2 K. Semiconductor. Electron mobility is one important parameter describing semiconductors because it describes the rate at which electrons can travel through the semiconductor. At 40 K, electron mobility ranged from 0.49 * 106 square centimeters versus at an Sb concentration of 0 to 24 * 106 square centimeters versus at a Sb concentration of 7.2%. This is much greater than the electron mobility of other common semiconductors like C, which is 1,400 square centimeters versus at room temperature. Another important parameter of bi-1xSbx is the effective electron mass, a measure of the ratio of the acceleration of an electron to the force applied to an electron. The effective electron mass is 002 me for x equals 11 and 009 me at x equals 06. This is much less than the electron effective mass in many common semiconductors. A low EEM is good for thermophotovoltaic applications. Thermoelectric bismuth-antimonides are used as the N-type legs in many thermoelectric devices below room temperature. The thermoelectric efficiency, given by its figure of merit Zt equals sigma S2T lambda, where S is the Seebeck coefficient, lambda is the thermal conductivity, and sigma is the electrical conductivity, describes the ratio of the energy provided by the thermoelectric to the heat absorbed by the device. At 80 K, the figure of merit for bi-1xSbx peaks at 6.5 * 10⁻³ K when x equals 15%. Also, the Seebeck coefficient at 80 K of bi 9Sb1 is minus 140 microvolts K, much smaller than the Seebeck coefficient of pure bismuth, minus 50 microvolts K.